Thank you.
The second invited talk for today is by Kristoffer Carlsson, who was a PhD student at Chalmers University of Technology before he started working at JuliaComputing as a software engineer. And he's currently living in Sweden. And he's going to talk about the three of the areas where Julia really shines, which is productivity, performance, and reproducibility. Kristoffer, the floor is yours.
Thank you, Samantha. Just checking, can you guys see my screen and my cursor?
Yes.
And hear me okay? Yeah?
Yes, all
yeah.
perfect.
Thanks. So today, my goal is to show you a little bit about the Julia language and why that might be useful to have as one tool in your tool belt. So a little bit of background about the Julia language. It was created at MIT and it's quite new. So it was first public released in 2013. 1.0 was released in 2018. And after that, there's no plan for more breaking changes for a long time. So your code should just keep working with newer Julia versions. It's a general purpose programming language, but it has some features that make it suitable for scientific computing. And I'll try to show some of those things. It's a num-focused supported project. It is JIT compiled, so the compilation of it happens just before a function runs, and we will see a little bit later what impacts that have. It's MIT licensed, so you can use it for whatever you want, basically. It's garbage collected, so you don't need to, explicitly free things and so on. The system keeps track of that. And one aim it has is to solve this sort of two-language problem, which is kind of defined as, you make a prototype in a productive language, but maybe it's a bit slow. And then when that works, you re-implement the whole thing in a fast language like C++ or something. So then you're basically doing the work twice. So the one idea of the Julia language is like you should be able to do this whole process in just one language. Just want to show a little bit of the syntax here, how the Julia looks. So here we have a struct, something that can contain other data. A circle, it contains a radius here. We can define a method acting on a circle. Here it computes the area. We can have another struct, which is like a rectangle here with some other data. And we can define another area method on the rectangle. Then we create a vector of these shapes. And then here is a special syntax to call the area on all of these shapes. And we get a vector back, which the different areas. So it's just a very short syntax example of how Julia code looks. So today I want to show why it's possible to use Julia as a research software engineer. And there are three things I want to highlight here: productivity, performance, and reproducibility. And if I have time, I have some just random cool stuff that I could show, but we'll see if we have time for that. So first, let's talk a little bit about productivity. So one thing that, let's say you come from Python, you expect some kind of basic functionality like data structures, like for example, arrays, dictionaries, and comprehensions. So here we can create a list with just some random things in it, integers, strings, and tuples. We can reverse it and so on. We can create dictionaries and access things in the dictionaries, and we can do comprehension and so on. So let's say if you come from Python, you will be fairly familiar with these type of basic data structures. And in addition to that, there's also quite a lot of linear algebra built in. So there's different solvers here. We can create a random matrix and do matrix vector multiplication. We can do backslash to do a linear solve. We can do more advanced things like SVDs. You can also create sparse matrices, and then there's solvers for sparse matrices and so on. So I guess this bottom part is gives you a little bit of a MATLAB feel. So if you come from MATLAB, you have all these kind of MATLAB things already in there. Or if you come from Python, maybe most of this you could use from NumPy, but here in Julia, it comes already. Second, there's a built-in package manager. So in Julia, there's only one package manager, fortunately. And what we do here in the REPL, we can enter a certain package mode. So if I press this button here, we go into the package mode REPL. So here I can start with what we call an empty project. We haven't added any packages yet. Then I can add some packages. The system installs those. We can see now when we do the status here that they are installed, the packages. And then we load a package and we can just use it. So this is sort of the workflow when you have something there which is not built into the language. You just add one of the many packages and you can just start using it. But let's say it's not built into Julia and it's not built into, there's no Julia package you can use it from. Well, fortunately, Julia makes it easy to call other languages. So a lot of great code has been written in C, but also R and Python and many others. But it's a little bit awkward to communicate between these languages. We could, for example, write data out to a file from Python and then you read it back into Julia. That's a possibility, but it's a little bit awkward. So Julia has quite a lot of tools to make it easy to go between languages like this. And there's a Julia organization here which has all of those packages in it. So I'm going to show a few examples here. So one example is calling it to C. And of course, every language needs to call it to C. A lot of things there are needed. So as an example, I'll show how to do this in Julia. Here, I have a C file here that does a simple, this simple XP operation. I can compile it here to a shared library. And the way I call it from Julia then is using the C call macro. So what I do is I give the name of the shared library, I give the name of the function, then I need to give the arguments here with types, because remember now we're calling it to C, so we need to give explicit types here so Julia knows the calling convention and can call it. We need to give the return value, and then we just return it here. So here I create two matrices and a number, then I call it in Julia like this, we get a number, and then I call this one here, and then it's called, as you can see, it says computation in C done, which is what the C library here. So I would say this is pretty easy to call C libraries from Julia. You just give the name and all the arguments and the types. And if you're wrapping a big library which has a lot of header files and so on, you can automatically generate these wrappers with a Julia package. Second great language is Python, and there's a package to call into Python. So it's called PyCall. So if you have some, if you code in Julia, but you have some Python code you want to call, that's no problem. You can just use this PyCall package. You can, for example, import the math library here. And now this here, math.syn is actually calling the Python sign version. We can do some more advanced things. We can import the SciPy optimized package. We can create a Julia function here, and then we can call the Newton solver inside of the SciPy package here. And we can see here that every time the Julia function is called, it writes out some stuff here, and then we get the result. So here we're calling a Python optimizer with the Julia function, and it kind of just works. You just pass it in as an argument here. You can also do some more advanced stuff with PyCall. We can use pyplot to plot, and if we want, we can also just write Python code here inside a string, and it's sort of similar to just working in the Python repo. Another great package from Python that we just heard about is Qtip, of course. So I'm going to show how, if you want to use Qtip from Julia, you can just use the Conda package, which Conda is a Python package manager, but you can use it from Julia as well. We can just add the Qtip from the Conda Forge channel. It will install here. We can import Qtip, and then we can start using it here. So here, now this is a Julia matrix here, a random one, and we can pass it into different Python objects, and PyCall will correctly translate from Python and back and so on. Another great language is, of course, R. A lot of good stuff in there. And then there's rcall for that, to call it that. So we can, when we load the rcall package, we can get a special R REPL mode. So it's kind of like we're in the R REPL. We can enter a thing here. Then we can pass the data from Julia here. So I define a foo variable, and I can pass it into R here using this interpolation syntax it's called there. Now you can see it's defined in R. We can get variables from the R session. We can put variables into R. So here I define Z and I put it into R, and then it's defined here in R. I can create a random vector and do like a t-test on it and so on. So it's pretty smooth going between Julia and R as well. And we can also do plotting in R, of course. So here I am loading ggplot, and I'm plotting some Julia data. So here, this is a Julia data frame that I'm plotting in R. So Julia then has to convert from the Julia data frame to R, but it happens pretty seamlessly here. Some other things that's nice to have is, of course, Jupyter Notebook support, just showing that it's available. Just as a fun fact, maybe some of you don't know, but the name Jupyter here is actually based on Julia, Python, and R. So that just works. One thing that I find pretty convenient when developing a code is this hot reloading. So there's a package called revise. And what happens when you use that is that if you change your source code, you can immediately run your function again, and it's updated the code. So here I'm loading revise and a package. And if I look what's inside the package source code, it prints hello world here. And I call it and it prints hello world. Then I go into my text editor and I edit this to NRSE. And now when I call the function again, it immediately updates the function here. So you can like run your code, update a little bit, run again immediately, and it just immediately updates. One cool thing about this is that you can also use it on the Julia source files itself. So if I load revise here and I tell it to track base, and then I just call a sign function, then if I edit the Julia source code here, I add a little info thing here. When I call the sign function again, now it adds this info statement. So I also develop a bit of the Julia code itself, and then this is very useful. You can just edit the Julia code, run it, and so on, back and forth. And you don't have to sort of recompile a big thing every time. It's just really seamless. One thing which maybe Julia has quite a lot of focus on is performance. So just say a little bit how the Julia compiler works. So it is a compiled language. So what happens then is that Julia code gets translated into something called LLVM-IR. And LLVM is a sort of a compiler framework that do a lot of optimizations and generate machine code. And this is not different, for example, how some C compiler does it, like Clang does exactly this, Swift does it. So there's no reason Julia should be slower than any of these compiled languages. They all do sort of the same thing. So let's just define a very simple function here to do some experiments on. So here's a function I call mySum. It initializes some variable, it loops over this vector that we put in, accumulates and returns it. You can define some random vector here and call it, and we get back a result. And then we can load the benchmark tool package, and we just write at benchmark here, and the benchmark tool package is going to run this code over and over again until it has a statistically good result. Here we can see it ran it 376 times. The minimum time was around 11 milliseconds, and you get a little bit more data. And then one thing Julia does is allows you to sort of introspect the generated code quite accurately. So we can use this code LLVM on the function. And what we get back then is actually the LLVM-IR here. So this takes a little bit of practice to read, but if we go down here, we can see here it sort of loads the element from the array, and then here it adds it to the accumulator, and so on. So this is LLVM-IR, which we can get with code LLVM. If we want to go even deeper, we can look at the machine code with code native. So then we can see here is the add instruction. It's an assembly instruction, the add from our accumulation. And then here is sort of when we're incrementing our loop counter and we're checking if we're going to edit. And this is sort of the same code you would see if you wrote it, this loop in C or something. There are some performance annotations you can use on functions. So you can add at inline and say that I want this function to inline. Sometimes that's useful for performance. There's an inbound annotation, which is basically says that I assume that this array access is inbound. Otherwise, normally if you access things out of bounds, you will get a bounds error and you'll get an exception. But in some cases, when you have a really hot loop, you need to be able to turn this off. But of course, if you use this wrong, then Julia might write to memory. Then you might get just garbage results. So this is like, it's a powerful thing, but you have to be careful. There's also the @simd annotation, which allows reordering reductions. So I took exactly the same functions I had before here and add simd here. We'll see what happens then. So if I again look at the code LLVM here for the simd version, you can see we have a bunch of these vectorized additions. And what that does is it's compute many additions at the same time, kind of using different operators. And if we look at the native, we get the same here. We get these vectorized addition assembly instructions. And we can see if we benchmark this, that we get almost 3 times the performance here from using this macro. The reason Julia couldn't do it by itself is that this slightly changes the result. You can see here, if you look at the end decimals, there's a very small change here. And an optimization is not allowed to change the end result at all. So you basically need to give an extra freedom here to say that it's okay to do this reordering and give a little bit different answer, but for good performance. There is threading here. You can use the threads macro to basically say that I want to do threading over something. So if you pass in some vectors here, so I'm saying I want to run this loop threaded, and then I run this loop with different number of threads. And if I run it with 8 threads, it takes 1 millisecond, 4 threads, it's a bit slower, and so on. So threading is sort of built in. Let's skip this. You can also do distributed computing. So you can add processes here. You can call like reductions on these processes. You can spawn tasks on different workers. So here I'm doing a loop here that I'm defining on all the workers, and then I can say, okay, I should spawn it somewhere there, spawn it on that process, and then I can get back the result and stuff like that. There's also, if your CPU is not strong enough, you can also go to GPU computing. So there's wrappers for CUDA, but also AMD and these newer things called One API, which is Intel's sort of CUDA version. So as an example here, how to use CUDA, we can use the CUDA and then I use some other package. I put a planet here, a struct with some mass and velocity, define an energy function for how to compute the kinetic energy, the total energy for a vector of planets. We just sum the energy of all the planets. Then I create some planets here in a vector and I calculate the total energy. Now let's say I want to compute this on the GPU instead. The only thing I have to do is to make this a Q array of the planets that will transfer the data to the GPU here. And now when I call this function on this CUDA array, it will run on the GPU. So I didn't have to like write any GPU specific code. All of this generic code could run on the GPU as well. It's also possible to write the explicit kernels in CUDA. So the sort of hello world example in CUDA is this vadd kernel where you just add two vectors. Here I can create some random data here, and then I can launch the CUDA kernel with some number of threads, and we can check that the CUDA version is the same as the CPU version. So you can also, if you need to really go deeper down, you can also write your own kernels. So finally, let's talk a little bit about reproducibility, or the ability to run your code again on a different machine 5 years later when someone asks you for your data and your paper or something like that. So the package manager has these things called a project file and a manifest file, which is sort of connected to every project you create. So here I have this Nordic-RSE project, and I can do status here, and I see some packages in it. I can also give the -m, and then I see all the transitive dependencies here and the versions. So the project file contains all your direct dependencies, and the manifest file contains all the transitive dependencies and their versions and so on. So if you just look what's inside these files, you can see here that the project file, they have the packages names here, and every package has a unique UUID. If you look at the manifest file, there's a lot of packages in there, but we can also see that there's a unique hash here for each package, which basically you can use to recreate all the versions of the packages and some other one. So to show how this, okay, and then there's also the question about binary dependencies. So some package manager take the approach that they download source and compile locally, and some ship sort of pre-built binary dependencies. Compiling locally on user's machine is pretty hard because they can be in all kinds of weird states, have weird compiler versions installed and so on. In Julia, basically a lot of the binary dependencies that people commonly use are cross-compiled for all operating systems that Julia supports on sort of dedicated machines. And then we ship pre-built libraries as just tarballs, so there's no compilation on user machines. So if I want to use Lua, for example, I can add this Lua JLL. It's sort of the common suffix for all the binaries. I can use this package, and then I can run Lua here, for example. And the way every package is stored is basically all these projects. Let's say I have a project from my first paper and my second paper. All of these have manifest files, which you remember they contained all the packages. But then the actual packages themselves are stored in like a central depot on the user's machine. And all of these refer to them. So if both of these projects use the same package version of something, they would just be stored once here. So I'll just show once how it would look if I want to reproduce my code on another machine. And that is what we call instantiating a manifest. So what I do here is I copy my Nordic-RSE Julia project to a remote machine. I SSH into that machine and I go into that project. Now I start Julia here. Now that's on the different machine that I want to reproduce my code, and I do the status here. What Julia will show here is some red arrows for packages that are not yet installed. And it will say that you can use instantiate to download these. I call instantiate, and Julia installs all of these. And now I can use Lua JLL on this other machine, and I can run it again here. And one thing here, the code I did was on a Mac, but what I uploaded to here was a Linux machine, but still I could use this Lua. So even though if you have binary dependencies, this instantiate workflow works pretty well. Let's see, how am I with time? Am I completely done or? I can just show really quickly some cool stuff. And so one cool package is unitful, and you can load that package here, and then you can basically use units in your code. So you can do 1 meter plus 2 meter, that's 3 meters. You can add, you say define some mass and some acceleration, and the force is equal to the mass and acceleration. Then you get this units here. If you try to add two things that don't have the same units, you get an error. You can also put these into structs. So if I have a person here, which should have a height, which should be meters, and mass in kilo, I can call this person with 5 feet and 10 inches and 150 pounds, and I will get it in meter and kilograms and so on. So this is pretty cool to use, for example, if you have some courses like mechanics course and you want to make sure that all the units come out in the correct dimension. Second sort of cool thing I want to show is automatic differentiation. So here I'm using a package called forwarddiff, and I define some function. And then what I can basically say is, oh, I want the derivative of this function. And then this function will now be the derivative. And I can plot it here. So I'm plotting the function and then the derivative here. And we can, for example, benchmark it. So the analytical benchmark here of this function is given here. And then I compare the automatic differentiation version and the analytical version. And you can see here that they're pretty much the same speed. So I didn't gain anything by defining the analytical version. I could just use forwarddiff here, and it gives pretty much the same performance.
Yeah, thanks a lot, Kristoffer. Sorry for jumping in here. So the reason why the chair didn't say anything earlier because her computer crashed,
Okay.
but the chair is back in a moment. And what I want to say is also encourage more questions, and thanks everybody for their questions and comments, and we will come back to them in the Q&A session later. And I mean, I didn't want to cut you short here. If you have like one more slide, you can conclude, and then after that. And thanks so much for your talk. Thanks for the slides. Let's link also the slides in the HackMD.
Yeah.
And we will take a 10-minute break and then return for, let me double check quickly. So after the break, we will do a Q&A session.